Hey guys, welcome back everybody. Today we're gonna do a system design practice interview. The question is design an online auction system like the Instagram auction or eBay. The very popular auction system, right? eBay. So let me make it this way for everyone to easily recognize that. So let me paste in the requirements. This is a really the high frequency system design question that's recently asked by a lot of big tech like Meta, OpenAI, Google, TikTok as well. So without further ado, let me paste in the requirement. What is the auction system? So an online auction service lets the user listen items for sale while others complete to purchase them by placing increasing highly bid until the auction ends, with the highest bidder winning the item. This is what the online system, right? So in on this system design, we'll have about 30 to 35 minutes to go deep dive into it. So what I'm going to do that I'm going to first list out all the functional requirements. What is we mainly focus on designing on this system. So let's get it out, right. Let me quickly listen down here to functional requirements. So my first functional requirement is that when we talked about the online auction, we need to allow the user to create a post, right? Create an auction post. So the user should be able to create an auction post. And my second functional requirement is after the user create an auction post, they go to the webpage, they create an auction post, they should be able to create auction post going to have the images, the description, what else? And then what will be the next functional requirement? The user should be able to go to auction post and they place a bid on the item, right? So user should be we're gonna support it as user should be able to place bid on an item, on a post item, and then where the okay. So I'm assuming that we only accept the highest bid, right? Okay. So my next functional requirement is that the user should be able to view an auction, should be able to view an auction, right? They're gonna view all the highest bid, the details, the about the items, images, link, description, including the current highest bid. The current highest bid. Okay, so these are my three functional requirements. I'm gonna focus on this systems. So I'm gonna list out our scopes. So my best practice for the best practices, right? These are I'm gonna clarify with the interviewers. These are the functional requirements. Are the one that I'm gonna focus on my system design for today, and the out of scope section that will be these are the one that will be I'm not going to focus on this for the systems. So if you like me to bring it up to a functional requirement, we're happy to. Okay. So one of the out scopes in here that users maybe like search for items, uh, doing like sort items, filter item, short or filter items, or we have like a auction history, right? of an item, right? Yeah, so my next section is that we're going to focus on a non-functional requirement here. So the non-functional requirement is where we emphasize how the system should behave, right? Whereas the functional requirement is emphasize the user should be able to do some take action in our application. The non-functional requirement usually emphasize about the system. For example, we talk about a CAP theorem here. CAP theorem means when the network partition happen, it could happen either on application layer or database layer. but it's always happen, right? Shall we favor the availability or the consistency? So on this system, because the bits gonna come in asynchronously, and then there's a million of users gonna bid on the system, right? So I'm gonna do favor the strongly consistency for the bits, right? Because when the bits comes in, it has to be properly updated and propagate right away to the users. So we need to place a strong consistency for bits. The next one is then we talk about what about the fault tolerance? We cannot drop any bits, right? So I'm gonna focus on fault tolerance here. Cannot drop any bits. Okay. What about the how do we display the bits to the client here? So it should be as real time as possible, right? So I'm gonna do a real time max bit display. So when the user try to bid in bid on the item, and whoever get the highest bid is gonna display the bids into an item in the real time. So real time max bid display on client. What about the scale here? What about scale? So I want to talk a little bit about the scale before I list out the non-functional requirements for this particular system. I'm gonna clarify with the interviewers what will be the scale of the system. What is the scale, right? So normally in here we're gonna have systems to be able to let's assume that the system should support 10 million um, daily active user concurrent auction, right? That's huge. Like eBay or Instagram auction, 10 million concurrent auction is happening every day. So we should talk about the scale to 10 million concurrent auction. Okay. So these are my non-functional requirement where my system should be able to achieve or behave. Okay. So now let's dive into the core entity of the system. The core entity is actually where we talk about the high level data models in our system, right? So for example, we can list. I'm gonna list out here. I'm gonna list out the high level data models and metadata. We're gonna go deeper into the metadata once we talk about the high level design. So here I'm gonna list out a table here. My potential tables, we're gonna have this auction, right? We have the auction post. In the auction post, we have the items. When we have the bid and also have the users to interact with the bids, right? Cool. So these are my quantity. Without further ado, let's jump into my API or like what I call it interface design. Okay. So in here, we're gonna design how we interact with how the user interact with our application. We will using the RESTful API for in the check of this system design. So my first functional requirement, I'm gonna link to my functional requirements. Users to be able to create an auction post. Create an auction post. So in RESTful API, we're gonna create a post endpoint, right? Because the post is gonna be submit a new record. So we create a new auction post, which means we're gonna use a post endpoint. We can list out some version of APIs in here, or it's optional here, right? So normally I'm gonna have the resources auction, and then it's gonna return to me all the information we want to the auction and the item that the item object that the user plays in the auction, right? So here, body, typically gonna have the item to be item object. We will have like start date for the auction, right? And also if we have the start date, we also need to mention about the end date, and also we need that starting price, right? And typically it's gonna be a number. Okay, cool. So my next functional requirement is that users should be able to place a bid on an item. Place bid on an item. We only accept the highest bid, right? So place bid on an item. On an item. So we can do actually post endpoints again, right? We can do post or batch endpoint. So in this one, I'm gonna focus on the post. Place with an item. We're gonna nest in a resource in auction, right? And also we need to paste in the auction ID, right? Because we need to know which auction that right now having the bits we have having fetching the bits into it. So it's gonna return to me the bit object. My body is going to return. We're gonna include actually the bit from the user, right? Cool. So what about the next one? We have users should be able to view an auction details, right? Let me down here view an auction details. Make it clearer. Okay, view auction details. So if you view an auction detail, you're gonna use the get endpoint where this is auction, right? We're gonna nest in the resource auction ID, and it should be able to returns me the auction and the item, the inside the auction. Great. So we complete we have three API endpoint, right? Which create an auction post, place a bid on an item, and view an auction details. So now we jump into the high level design where we're gonna sketch out the high level design of our application. So let's start it out, right? We're gonna start with the client here. When a user or the client they create an auction post because or wait a minute, because we have the multiple action on from the user right now. They have to create an auction post, they place a bid on an item, we want to view the auction details, right? So I would opt for using the two-phase architecture here, which is, we're gonna have the API gateway to handle like a the microservices. So let me put it out here, API gateway. We can use API gateway like OpenAI, AWS API gateway. Okay, we can use that. In here, usually it's gonna support as a mid layer for to routing a request. We can have the SSL authentication, the load balancing. They have the rate limiting. They have the built-in functionalities, right? When the most important function has support is the routing. Okay, so when the client sends a request into the application, the API gateway is gonna route a request to create auction post. So I'm going down here. It's gonna have a auction service, right? Or the cross service, right? Auction service. When the user go here, you're gonna send a request or post an item. Post an auction, right? You're gonna send a request to create a new auction post into auction service. Once they receive the request, they're gonna update our database. I'm gonna name a primary database here. Okay, auction service gonna go here, checking. We're typically gonna check if the auction already exists or not. If it already exists, it's gonna notify the user, hey, you need to update. You need to create a new auction, but it seems like it's already existed. Otherwise, we're gonna create a new one. Which is create a new one into our database record, right? So normally you're gonna create an auction. Typically, we're gonna create an auction table with the metadata like auction ID, we have the ID, the item ID, right? ID is the primary key. We have the item ID. We have the start time, the end time, the creator, right? We know to know creator ID as well as the starting price. The dot, we're gonna list out here, right? In the real world, there will be a multiple more metadata, so I'm gonna list out as a dot. Okay. So another table we're gonna interact with is gonna be the item here. When we have items, we're gonna have the ID. We will have the name, the description, the images of the item as well, right? Image. We can list it like the S3 URL link rather than storing the whole image into it. So dot as well for all the metadata. Cool. So this one we already achieved the first functional requirement, right, which is user should be able to create an auction post. So what happened is when a client send a request to create a new auction post into our application, the API gateway gonna check the authenticate it, check the rate limiting, and also route the request into the auction service. Once we receive the request, the auction service is gonna check whether the auction post already exists in our database. If it is, we're gonna prompt the user to create a new one, or either create a new one or add it to the existing post. Otherwise, we're gonna create a new record into our auction table here with some metadata like metadata like ID start new item ID with a new item, start time, end time, creator ID, and a new starting price initially that the user put into it. Okay. And that typically have a relationship between the auction and the item, right? Because one auction can have multiple items. So at that point, I'm gonna opt for using the Postgres because first, I want to talk a little bit about here, right? It seems that we have a lot of relationship between the auction and items because one auction can have multiple items, and we're gonna have a bid table. We have a user as well, and user can place multiple bits into the item. So to empower this relationship, we can use some source of SQL database, right? AKA like RDBMS, like a relational database management system. And also, since as the system required a strongly consistency for bits as my first functional requirement, and the nature of Postgres that is really strongly consistent. Right nowadays, DynamoDB is also supporting strongly consistent, but on this system, we're gonna dig in more into that. How do we use a strongly consistent is really useful when we use if we opting for using PostgreSQL. Okay. For now, for high level design, let's keep it that way. Okay. So my second functional requirement is that user should be able to place the bit on an item. Okay. So my placing the bit on item is going to be something like you have the bit table here. Okay. Bit service, right? So when a user places the bits on a service here, they create a post with the auction and the auction ID, right? Great. They're gonna create. So clients place a bit into the item, right? They at the auction post right now. They're gonna place an item, the bits into that item. API gateway is gonna route a request into our bit service, and afterwards, the bit service gonna go to database here. All right, checking the starting price on the auction table. If it's higher than that starting price, we're gonna create a new record here with the bit table here, right? With the ID, the auction ID, all right? We need to know the auction ID. Let me zoom it a little bit better. For the auction ID, we need to know the price, the current price, the highest price actually, and create it at where the user submitted, when the user submitted ad, and also the status. The status could be either to accept or it should be able either to be accepted or rejected, right? Because we're only accepting the highest bit. So let's say for example, right, one uses a bit like $50 for item A, right? Again, API gateway gonna route to request into the bit service here. Bit service is gonna check in. Once you receive the request, you're gonna check the starting price. You're gonna compare with the starting price in the auction table. If it's higher than that, you're gonna create a new record in the bit here with auction ID, update the price, update, create a field, and the status will be accepted. Return it back to the user. If it's not, the status will be rejected, and prompt the user, hey, you have to enter a new higher bits. Okay, this is how it works. Okay, cool. What about the we're an auction, right? So we can utilize out here, like we're gonna have the get auction of well, get auction with, we can utilize this one, right? As a something like we can encapsulate it. We can, okay, we can divide to the microservices. So right now we have create auction. So let's name it create auction. And now we have to get auction, which means the user want to view an auction details. They're gonna go to request, go to auction service. So auction service is gonna go fetching all the related information in the auction table, and we can normalize data by joining the item data and the bit, right? And from a user as well for that particular user ID, and return it back to the client with the whole auction details and the history. Okay, right here we're gonna have like a create or submit bit. So create bit. Okay. So this is our highly functional requirement. We successfully achieved like 3 functional requirements in here. Let's dive into our let's go to the deep dive, right? Deep dive part. So normally right here, let's make it better. Okay. So right now for the deep dive part, I want to talk a little bit about the first non-functional requirement, the strong consistency for bits, right? Let's talk about it. So let's talk about the strong consistency for bits. This is a deep, I can see it. Okay, so this is deep dive part. So we'll talk about the first point, that strong consistency for bit. Okay, so let's talk about it right here. So when the user submit the bits, we go to the auction system, and when the users create a bit, let's assuming one scenario that we have 2 users. User A submit the bid for $10 at the 10 a.m. right? The highest bid right now is going to be only $5. So the bid service will receive the request and go to primary database, updating the highest bid to be the $10 at 10 a.m. Right? Status now right now is to be accepted as primary user A. Hey, your bid has been accepted, and now use at the same time, simultaneously, user B submit another bid at $20. Let's go to the bid service, right? You're gonna go to the database. So since there are some delays on the data, so this happening that the Postgres still realizing the $10 is the highest bid, but the $20 right now is coming, right? And he didn't realize that this is the highest bid, so they sending out the $10 is still the highest bid, where it's supposed to be the $20 right now to be the highest one, right? For to be accepted for the user B. So I send out a rejection back to the user B. So right now so in that scenario, we don't want it. We need to have the bits to be strongly consistent. How can we do it? There are multiple ways we can do it, right? The one option we can do actually using the locking mechanism, aka the optimistic concurrency control. So it's the acronym for it's going to be OCC. This is known as the locking mechanism. Okay, so basically, when a user submitting the bid, right, it's going to lock that row. For example, user A submit $10 bids on item A on the auction post A. Is in Postgres, it's gonna lock that rows. You're gonna check in the auction right now with the starting price at $5. Now $10 is higher than $5. We lock the row. We compare when we accept. Hey, $10 is the highest bid. Then the status will be accepted and return it back to the user. Hey, let's to say that we accept the bid. The bid is right now is $10, and then we release in the lock. That's how it is. Okay. So something that we can do is actually begin the transaction, right? So it's gonna be locking the rows. I think it's in locking the row, right, on the transaction when the transaction happen. Okay, it's gonna compare, gonna check if the bid, a submitted bid is higher, is the highest bid is greater than the starting price or the current one, current bid. If so, then update the status to be accepted or rejected. Then update user, and commit, right? Yeah, update user and release the lock. Okay. What about the second option is that we can talk about another option we have is to ensure we have a strong consistency for the bits is actually is we have well, actually this is a pessimistic consistency or a pessimistic consistency control. Okay. What about pessimistic consistency? We want to talk about OCC, right? OCC is a optimistic concurrency control. This is a BLS BCC, where this one is a OCC, right? This is a optimistic concurrency control where we will have this is gonna be keep checking the bits until is this updated or not. If we keep checking the bits until it's updated or not, right? So for example, like we begin the transaction here. Okay. Then it's gonna keep checking until the business is established or not. Right. Okay. So let me talk about, right. We can cast it or those, right? Or so let's talk about the OCC, right? The OCCs mean that it's faster. However, it's happening when the bit conflicts are rare. Better performance, but when the the bit conflicts are rare. Conflicts are rare. Because most bit won't happen simultaneously on the same auction. Most bits won't happen simultaneously on the same auction. Okay, here's how it works, right? So we start by the read the auction post. Okay, here is how it works. We're gonna start by read the auction post, auction row, and get the current max bid. It read the auction row and get the current max bid. And then it's gonna validate. Let me note that to be first step. The second step, we're gonna validate that bit. That the new bid is higher. Is higher than the max bid. If so, then we try the update auction row. But only if the max bid hasn't changed. So we can do something like an update in SQL, right? We're gonna do some update auctions, and then we set auction when we set where the max bid is gonna be equal to a new bid, right? We paste in a new bid, that's where the ID is equal to some auction ID. and the max bit is the original max bit. Max bit, right? Yeah. So if successful, so if this is update succeeds, then we're gonna write the bit record. Okay. If it fails, we retry from step one. Fails, retry from step one. Cool. Very cool. So this approach actually avoid locking mechanism, right? And still maintain a consistency at the cost of conditional retries when the conflict do occur. So we need to add the max bit price into the auction, right? We beat the auction when we get the current max bid, and then it's validated that the new bid is higher than the max bid or not. If so, we try to update the auction row, but only if the max bid has not changed. Only if the max bid hasn't changed. We can do something like update auction, and we set the max bid equal to the new bid, with the ID equal to the auction ID and the max bid equal to the original max bid. If the update succeed, we write a bit record. We write a bit record into the bit table, right? Otherwise, we will try from step one. With the auction row, get the current max bid, right? And then validate the new bits is higher than the max bid, right? If it's so, we're gonna try to update a row, and only if the max bid has not changed. But only if the max bid hasn't changed. Okay. And my third option that I wanna bring it out is actually the Postgres has the default option for the default isolation level that really have a they support the default isolation level. To ensure the strong consistency for the transaction. That's it on the transaction. Okay. Cool. What about the next one? This is the best semester Joe. Okay, so let's talk about that, right? So we have to talk about the strong consistency for the best. Let's talk about fault tolerance cap, which means we can fault tolerance. How do we ensure that the system is fault tolerance and cannot drop any bits, right? So let's introduce it, right? The bits can happen in here quite a lot. Let's say we have the 10 million concurrent user 10 million concurrent auction happening at the same time. So right now there's a lot of the business is going to be easily overwhelming. We don't want it. So I'm going to want to introduce a highly reliable and fault tolerant solution. We can introducing some basic queue like that, right? And then we can have some. Initially, it's gonna have some producer to actually receive the bits right away when the user submit the bit, and then it's gonna actually it will it will it will enqueue in the producer is gonna enqueue to the Kafka queue right away, right? This is my Kafka message queue. This is Kafka. I'm gonna name it like a message queue, right? It's gonna enqueue right away into my message queue, Kafka. Okay. Let's make it one-way error. Okay. So the producers, when this user submit the bit, producer gonna receive the bits, enqueue the bit immediately into the Kafka queue. Then the bit service is gonna act like a producer, right? It's gonna go to the queue, consume the number of bits, and then further processing the request into the database. This will it will make sure, it will help us to make sure that we don't drop any bits in here. So that's a good idea, right? So here I'm gonna talk about a Kafka queue, right? As a message queue, introducing a Kafka as message queue. So what happened is when the user submit the bit, producer, it will add to producer, add it to producer, and then in queue and publish to the in queue to the Kafka queue, message queue right away immediately. The bits service. So we will consume the bits and further process the bits to the auction in our data store or database, right? Okay, great. And how do we make sure that for now we're gonna we already have the, what about the delivery semantics, right? Let's talk about the delivery semantic here. So how do we doing with the Kafka delivery? We have 2 or 3 options, right? First one is actually exactly once semantics. Exactly one means is only producer and consumer only accept one request at a time from the queue. So right now it works performance, but it ensure no duplication message on the message, no duplicated message on the message, right? Where we have the at least one delivery semantic is better performance, but potentially duplicated. We need to have how do we ensure, but we can remedy, right? Remedy the probability of duplicate messages by actually adding how do we remedy the probability of the duplicate messages here? By adding the random number to the message, right? To the message or the user ID, right? Yeah, we can remedy that. Okay, what about the next one? We're going to talk about the real-time max bit display on the client. So here we have the Kafka, we have the bit service, right? How do we know that when the bit is updated, get accepted or get rejected, or even worse, get rejected? How do we update the user in real time? Okay, so we talk about a real time bit display on the client. So we can use some sorts of notification service, right? Now we can use a push notification like SNS or the Android push or the iPhone push notification service, or we can use a lot of networking things, like we can use or using, let's talk about like or using notification service, right? Or using WebSocket or the service and events. So on this one, I'm gonna opt for using I'm opting for using service and events SSE, right? Due to the due to the following reason. Is secure. No, it's not secure. Both of them is secure, right? It's a one-way or unidirectional communication approach from server to client, right? Is saving resources and the bandwidth over networking. Again, comparing against to WebSocket, right? And which will require more overhead as well, complexity. Okay, so we can here having the WebSocket, the server-side event to trigger when there will be an update to the client. So I'm going to use service association here, server-side events. Awesome. So how do we maintain once we the next one, right? How do we scale to 10 million concurrent auction here? How do we scale to 10 million concurrent auction? Okay, oh, so let's talk about the first one, application layers in here. So we can easily scaling for application layer, right? Application layer, as we utilize, since we use a API gateway, we can utilize, we can leverage using the load balancers, the built-in load balancers in load balancers to distribute the traffic, distributing the traffic to our micro services, right? And here we can scale. Let's talk about the massive queue Kafka. Okay, we can scale out the producer to horizontally by adding more micro servers instances, right? Servers, not service. Okay, so we can scale bump like that, and we can scale it up to a lot of, because hold on, because those are the micro tiny servers, so it's easily to scale it up as well. Okay, this is my producer. Easily to scale. How do we scale the Kafka queue? What about the Kafka queue, right? How do we scale it up? We can partition the Kafka, right? The Kafka master queue, but by obviously we're gonna partition by the auction ID as a more natural choice. Okay, and how do we know that when multiple instance, right? Oops. I'm gonna add it down here, partition by auction ID. So let's talk about the hot partition, right? So hot partition means how to prevent the hot partition issue. Hot partition, aka celebrity issue, right? Celebrity issue. What it means, like when we partition the Kafka, it's going to be multiple instances into it. So let's say we have a really popular items, or from the ancient, or from the Chinese ancient cultures, and there's a lot of people try to get that, right? I shouldn't say that, but let's say we have really popular items, like a limited Nike Dunk shoes, and a lot of people try to bid on the item and then try to get them. So that will create a lot of issue to overwhelm a single partition server instance in the Kafka queue, right? How do we remedy that? So we can the one way we can remedy that, by by adding random number to the partition key, partition ID, right? For example, right? For example, we have like we're gonna add like a auction ID to the n, where n is the number of partition in the number of partition servers. Okay. Great, cool. And by the way, we can scale horizontal scale and horizontal scale a horizontally scale link the bit service as well. We're already scanning group. Maybe trigger by 50% on a health check. Okay. It's gonna be something like that. Great. But that we I think we were running into another issue, is that we have the Kafka partition here. How do we ensure that the partition the auction ID, when a bit comes in here, is going to be matching with the bit instance in the bit service, right? How do we ensure that? But how do we ensure the this when partitioning will remain on the same instance, server instance of bit service? Okay, one way we can remedy that by we can use a PubSub, right? We can use a broadcasting services like PubSub, like PubSub, to ensure that the communication is going to propagate one connection is going to propagate to all the server instance, right? So for example, here we can have the PubSub here. Okay, the PubSub service is going to be getting the connection here. Okay, and then propagate it to the correct oops, over here. Okay, so what happened is, when the PubSub is gonna keep broadcasting the events based on the connection. Let's say the connection 1 to the server 1, but then the PubSub is gonna broadcasting the connection 1 on the server is sending event 1 to the server is servers 2, 3, and 4 as well. So in that way, we're gonna keep remaining the connection, persistent connection internet, right? To persist, to keep the persistent connection, the based on persistent connection. Great. Okay, and how do we scale the database? What about the database layer? Database layer, in this case in Postgres, right? How do we scale it? So we can use a we need to do some math, right? 10 million concurrent auction. One bit is going to be very small, right? It's going to be around 100 kilobyte something. Yeah, 100 kilobyte multiplied by the 10 million concurrent auction. A 10 to the 9 is going to be a trillion of data here, right? So 10 million concurrent auction. 10 million multiplied by 100 kilobyte on the message, right? So it's gonna be about 10 times 10 to the 6 multiplied by 100 times 10 to the 9 to the 3. So that would be 1,000 multiplied by 10 to the 9. that convert that to a trillion, right? 10 to the 6 is billion, 10 to the 6 million, 10 to the 9 is trillion, and we multiply by 3 again. There will be billion here, so it's going to be 1 trillion databyte data, right? So 1 trillion databyte data is not that much. We don't need to short the data, right? So we don't need to short the database. But in case we want to short the database, we can short the data by using the consistent hashing mechanism to maintain to ensure, not to maintain, right, to ensure the correct server instance on the same bit and auction instances. Great. This is consistent hashing mechanism. Okay. Observability, and we can talk about the ops, right? And monitoring. Monitoring, we're gonna substitute to the system here, so we can use a P95 latency. Can we observe P95 latency? We can observe the Kafka latency. Right? Kafka latency, consumer lag or something on the bit service, etc. Right? And then we can monitor the database lag as well. And can have some fraud detection. Detection to detect the multiple bits, the bit violation on the same identical IP address, or use a machine to detect that. Okay, cool. So we already finished our system design. We designed the online auction system like this Instagram auction or eBay. I know it's a really long video. It took like 52 minutes, more than 52 minutes, right, to keep it design. So we have, the goal is that we only have 40 minutes to design this comprehensive system, but we over around 12 more minutes. So I need to work on the timing as well, time management as well. But however, we successfully complete the functional requirements. We meet the target for all non-functional requirements. We cover all the non-functional requirements in the deep dive part, where the system is strongly consistent for the bits. We break it down, talking about all the options that we can support for the consistency in the bit to be strongly consistent. We also talk about how we have the fault tolerance in the by introducing Kafka. We talk about a real-time bit display by leveraging the SSE service and events. We also dig in to how do we scale to 10 million concurrent auction, where we scaling out from how do we scale our system from the application layer. Introduce a load balancer here, scaling out our our service microservices, scaling the Kafka queue, also scaling out the database layer as well. So I hope you enjoyed it. If you have further questions, please feel free to let me know. Otherwise, I will see you soon to the next system design question. As always, take care. Peace. Bye.